Welcome to lecture number 12 of my series on advanced mathematical physics, which covers differential geometry and will cover perhaps algebraic topology in the future as well. In this lecture, we are going to meet a very important entity in differential geometry, something which is especially important for physical applications, the concept of a vector field. Now, a vector field X on a manifold M is a map that assigns to a point P of M a vector in TPM. So a vector which is attached to the point P. So X of P is also denoted by X sub P, and it's a member of the tangent plane to the manifold at the point P. Now X may or may not be globally defined. It may be defined only over some subset of the manifold M. But for convenience, we will essentially consider most of our vector fields to be defined all over the manifold. If it's defined only over a part of the manifold, then whatever we are saying essentially will be restricted to the domain of that particular map X. So, one important way to characterize a vector field would be the following. It's a map from M to Tm, but with this additional property that if you compose it with projection operator following X, you are going to get back the identity on M. So if you take any vector, take any point P on M and apply the vector field on it, since you are going to get a vector which is in TPM and hence also in Tm, if you apply the projection operator to that, it just gives you the point to which the vector is attached. So it gives you back the point P. Therefore, pi composite X is the identity map on the manifold M. Now, just as we can think of a vector field as a map from the manifold M to the tangent bundle Tm, there is an equivalent way of looking at vector fields as a map which acts on C infinity M to produce C infinity M. So something which acts on functions, smooth functions, to produce new smooth functions. Strictly speaking, this should be a different map. Of course, X has M as its domain and Tm as its range, whereas this new map has C infinity M as both its domain and range. So it's obvious that strictly speaking, mathematically, we are talking about two different kinds of entities here. However, the second version of vector fields, the one which sees a vector field as a map which acts on C infinity M to give you a C infinity M function, is exactly equivalent to this particular version that we have talked about right now. And though strictly speaking, we should perhaps use a slightly different notation for that one, maybe X tilde to remind you that it's related to X, but it's really a different map. We will not bother to do that. We will just use the symbol X for the vector field, no matter which avatar of the vector field we are talking about. So, vector fields essentially come in two avatars, both of which tell you exactly the same thing. One is equivalent to the other, so given one, you should be able to figure out the other. In one, it attaches a vector at a point P to every point P. In the other, it acts on functions to produce new functions. So let's see how the second version of the vector field actually works out. Now, of course, when you say a vector field acts on a function to give you a function, in order to specify this map completely, you have to tell me what every function in C infinity M maps to under this X. Now, since this new thing, this entity which we are going to call XF, is also a function, the way to specify what function you really have is to tell me exactly what value it returns at a point P. So basically, what we need to do is to talk about XF at point P in order to define what X changes F into. And there is one very obvious and natural way to define this value of XF at point P. Remember, X being a vector field has a value at every point P and the value is a tangent vector, a member of TPM. Also remember that tangent vectors are really functionals which eat up functions and churn out numbers. So because you want xf to be a function on the manifold, something which takes in a point in the manifold and gives you a number, the most obvious and indeed the only relevant way of defining it would be in the following manner. xf at point P is defined to be x at the point P, xp, this tangent vector field, given f as an argument. Since xp is a functional, this whole thing here on the right hand side is a number. So xf takes in a point P of the manifold, produces a number, which is exactly what a function on M is supposed to do. So in this avatar, what x does is that it takes in a smooth function and produces a function. What I said a while ago is not really strictly speaking correct. X is not a map from C infinity M to C infinity M necessarily. It's a map whose domain is C infinity M. After all, the vector fields that we have will give rise to tangent vectors which act on smooth functions. However, the resulting function may or may not be smooth. Indeed, we will focus on vector fields of a special kind which do act on functions which are smooth and produce functions which are smooth. These are the so-called differentiable vector fields, but we will come to that issue later. For the time being, let us take a look at some properties of this x viewed as a map from C infinity M to the set of all functions on M. The first thing that we see is linearity. That is, if f and g are C infinity M functions and a and b are real numbers, then x acting on af plus bg. Let's take a look at what this function is. And once again, to figure out what a function is, you have to tell me what it does to every point on the manifold. So let's take a look at x acting on af plus bg. This thing in this bracket is a function, and you have supplied p, an element of its domain, to it. This is a perfectly arbitrary element. Now, by definition of x acting on a function, this must be xp, x at p, eating up the function af plus bg and producing a number as a result of that. Now, xp itself is a member of TPM. It's a linear functional. And because it's a linear functional, the result for this is simple. You get a times xp acting on f plus b times xp acting on g. But now notice xp acting on the function f is by definition xf's value at the point P, and this is by definition xg's value at the point P. So what you have here is a times xf at the point P plus b times xg at the point P. Now, since this works for all points in the domain of x, wherever x is defined, you can simply drop the p from this relationship and just claim this as a basic property of a vector field, that when it acts on af plus bg, it produces a times xf plus b times xg. An even more interesting property of the action of a vector field on functions comes from its action on a product of two functions. X acting on fg at the point P. This, of course, is a function within this bracket here, and that acts on this point P. But once again, by definition, this is nothing but xp, the tangent vector acting on the product function fg. And for a tangent vector acting on a product function, we have the derivative rule. This has to be f of p times xp acting on g plus xp acting on f times g of p. The fact that xp is a member of TPM is signified by the fact that you have f of p and g of p, the values of the two functions at p sitting as coefficients here. But once again, xpg is nothing but xg at p, and xpf is nothing but xf at p. So using that, we can rewrite this expression as f of p times xg of p plus g of p times xf of p. But now remember that the definition of the product of two functions is simply fg at p is f of p times g of p. So what we have here is simply the value of the product function f times xg at p, and this is nothing but the product function g times xf at p, which is exactly what is written here. Once again, this is true for all points p in the domain of x, and therefore we can just drop the p and write x's action on the product function fg is f times x of g plus g times x of f. And for obvious reasons, we call this the derivative property for vector fields. This looks exactly like the Leibniz rule for treating the derivative of a product of two functions. So we have seen that if we treat a vector field in this particular avatar, in which it acts on smooth functions to produce functions, we must have the following properties of linearity and the derivative property. Conversely, if we have a map which maps smooth functions to functions from M to R, the set of which I've denoted by phi M comma R, then this map which maps f to another function xf is equivalent to a vector field, and for the time being I'm going to refer to that vector field as x tilde, if the following properties hold. That is, this particular map is a linear map, and x acting on fg produces fxg plus gxf. This actually is a very great way of identifying whether certain maps are vector fields or not. Note that when I say x tilde is equivalent to this, I mean xf's value at the point p will be given by x tilde at p, which is a vector acting on the function f. Now what we really need to check is that x tilde p really is a vector at the point, that is, it is an element of TPM. First of all, in order to qualify as an element of TPM, you need two properties. One of them is linearity, the other is the derivative property. If x tilde p acts on AF plus BG, then by our definition here, this is how you defined x tilde p in the first place, is going to be x acting on AF plus BG, this function's value at p. And of course, because of the property that we have assumed for x, this is going to be AXF plus b times xg, this composite function's value at p. And the definition of a sum and product of functions is given in a particular manner, and that immediately guarantees that you are going to get a times xf at p plus b times xg at p from here, which can be rewritten as a x tilde p acting on f plus b x tilde p acting on g. So the linearity part is settled. X tilde p really is a linear map. Now what about the derivative property? If x tilde p acts on fg, again that's the same as x acting on fg at p, and by our assumed property x at fg is fxg plus gxf, its value at p is by definition f of p times xg at p plus g of p times xf at p, and now once again this is really f of p times x tilde p acting on g plus g of p times x tilde p acting on f, which is exactly the derivative property. So x tilde p has been established as a member of TPM, and therefore x tilde assigns to every point p in its domain a vector attached to that particular point. So it's a vector field. And although we have been careful in this part and denoted this vector field by an x tilde, whereas x was the map which maps smooth functions into functions, we will usually not make this distinction, and we will denote both these avatars of vector fields by x, the same letter. Let us now turn to the special kind of vector fields that we have referred to before, the so-called smooth vector fields. A vector field X is called smooth or differentiable of class C infinity if for all functions f belonging to C infinity M, the function xf that you get by the action of x on f is also a smooth function, that is a member of C infinity M. We can of course talk about x being differentiable of some class Ck as well, but those are really of limited importance, especially as far as physics is concerned. So we will focus primarily on differentiable fields or smooth fields, C infinity vector fields. Now, the set of all smooth vector fields on M is denoted by this rather crazy looking symbol as really the fracture X of M. And this is really the collection of all differentiable, by which I mean smooth, vector fields. A natural question to consider now would be the question of combining vector fields with each other. And we will stick to just smooth vector fields for the time being. So let us consider a situation where x and y stand for smooth vector fields. That is, they belong to this fracture X of M set. In addition to x and y, we have two real numbers a and b in the following, as well as smooth function f. Now, given a and b real numbers and x and y smooth vector fields, we can define ax plus by to be a vector field whose value at the point P, which we denote by ax plus by at P, is defined to be a times xp plus b times yp. We also define the product of a vector field x and a smooth function f times x, to be the following. It is defined to be a vector field whose value at the point P is given by the value of the function at the point P times the value of the vector field at the point P, that is, the tangent vector of TPM. Now, of course, the way we have defined this, we have talked essentially about the avatar of the vector fields in which they map M to Tm. And of course, since here ax plus by and f of x, f times x, both return at the point P a tangent vector at point P. This is of course a linear combination of two tangent vectors at point P, and TPM, the set of all such tangent vectors, is a linear vector space, as we already know. And this also is just a multiple of a tangent vector at a point P by a number, the value of the function f at P. So these are both, by design, maps from M to Tm, which is attached to every point P of the manifold a vector at that point. So these are vector fields according to our first definition of vector fields. Of course, this means that you can also think about these entities ax plus by and f times x as maps which carry functions to functions. And because we are dealing with smooth vector fields, we expect them to carry smooth functions to smooth functions. Now, to verify what happens in this particular avatar of the vector field, the one which maps functions to functions, we just follow the definition. Ax plus by acting on a function f gives rise to a new function whose value at the point P is simply the vector field ax plus by's value at the point P, this tangent vector, eating up the function f. And by definition, ax plus by at the point P is given by a times xp plus b times yp acting on the function f. And the addition of vectors is defined to ensure that this gives you a times xp acting on f plus b times yp acting on f. Note that this is really how the addition of vectors, or in general the linear combination that we are seeing here, is actually defined. Now, going backwards after this stage, xpf is nothing but the function xf at the point P And ypf, of course, is the value of the function yf at the point P. So we see that ax plus by acting on f gives me a function whose value at a point P belonging to the manifold is given by the value of the function a times xf plus b times yf at the point P. And therefore, we can say that the function that you get when ax plus by acts on f is a times xf plus b times yf. So the action on a function is also quite natural here. Now, if x is a smooth vector field and f and g are smooth functions, we can now begin to talk about gx, this vector field, acting on the function f. Again, we need to take a look at what this function returns when you feed it a point P as an argument. By definition, it has to be gx's value at point P, this tangent vector eating up the function f. But by our definition of gx at the point P, it is nothing but g of p times xp eating up the function f. And xp eating up the function f is nothing but the value of xf at p. So gxf at p is nothing but g at p times xf at p. So it's nothing but the product of these two functions g and xf evaluated at the point P. And once again, because this is true for all p belonging to at least the domain of x, if not all of the manifold, we see the gx acting on f is nothing but g times x acting on f. So these two very natural properties follow from the basic definition. We next turn to the fact that vector fields actually map the manifold or parts of the manifold into vectors stuck to those same points. And therefore, we should be able to describe these vector fields in terms of the basis vectors which describe the vectors at each point. Now, given a chart u, phi on the manifold M with coordinate functions x1, x2 up to xn, we naturally can define n vector fields written del xi, which are naturally defined to be vector fields whose value at the point P is nothing but the ith coordinate tangent vector passing through the point P. Remember that these are nothing but the tangent vectors to the coordinate curves, in particular the ith coordinate curve passing to the point P. Now, for any function f, which is a smooth function, the action of this del xi on f will give us a function, a new one, whose value at the point P will simply be given by del xi p acting on f. Note that this is nothing but the tangent vector to the coordinate curve, and using that fact, we had established earlier that when del xi p acts on the function f, it gives you a value which is nothing but the ith partial derivative of the proxy function f composite phi inverse at the point phi of p. Now, the left hand side here is expressed as the value of a particular function at the point p. So it would be nice if we could write this as a function on the manifold which takes p as an argument. But that's pretty easy. If you just consider the composition of the function dif composite phi inverse with the function phi and apply that to p, you're obviously going to get this. In other words, the action of this del xi vector field on a function f is simply given by the partial derivative of the proxy function composed with phi. So if you look at this as a function on the manifold, its proxy function del xi f composite phi inverse is nothing but the ith partial derivative of the proxy function corresponding to f. And once again, let me remind you of something I have said several times during the course of these lectures, The proxy functions are usually the way in which we express functions on a manifold. So basically what we are saying is the ith partial derivative of whatever stands for the function f is basically whatever stands for this function del del xi f, which actually justifies our notation del del xi for the basis vectors, because that ultimately is what we are really doing, taking the ith partial derivative, not directly for the function on the manifold, because we cannot do calculus directly on the manifold, but on the ith proxy function. And note that this is a composition of two smooth functions. F composite phi inverse has arbitrary partial derivatives because that is what f being smooth means. And not only that, its partial derivatives are also C infinity functions. Phi is by default a C infinity function by definition. And so this is actually a smooth function. In fact, what we are going to do is we are going to denote del del xi f, the operation of the vector field del del xi on this function f, simply by del f del xi. But we must keep in mind that when we say del f del xi, we really mean a function whose proxy is the ith partial derivative of the proxy function, or basically a function whose value is given by di f composite phi inverse composed with phi. Now, since these del del xi's with I running from 1, 2 all the way up to n, at a point P gives us the basis vector field del del xi P of TPM, it's obvious that we should be able to write any vector field x in the following form. X is of course given by what it returns at every point P of the manifold, or at least every point P of its domain. And that of course is a tangent vector belonging to TPM. So I should be able to expand that in terms of del del xi p's with coefficients which would of course depend on the point P, because at different points you get different vectors. So now notice that del del xi at P is nothing but the value of the vector field del del xi at P. And so this is the product of a function xi and the vector field del del xi according to our definition of a product of a function and a vector field evaluated at the point P. And since this works for all points P in the domain, we should be able to write x is equal to xi del del xi, at least within the intersection of the domain of the chart U and the domain of x. Now, there is a very easy way to figure out what these coefficient functions xi are. Note the distinction between tangent vectors and vector fields. For tangent vector xp, you expand that out in terms of coefficients which are actually real numbers times basis vectors. A vector field x actually has a very similar expansion, but there the entities here which stand in for the basis vectors are actually vector fields, and what you have as coefficients are actually functions whose values at the point P gives you these coefficients. Now there's a quick and easy way to determine this function. If you just look at the vector field x, capital X, acting on the ith coordinate function, capital X xi, that should give you a new function. Its value at the point P is nothing but capital XP at xi. But capital XP, which is a tangent vector, can always be written down as xjp del del xj at P. Note that I have to change the dummy index from I, which it was in the previous expression here, to j, simply because I don't want to confuse between the dummy index of summation and the actual free index xi sitting here. Okay, so what we have is xj at P, a function, times actually the value of a function, times del del xg at P, a tangent vector, eating up the coordinate function xi. But as we have already explained before several times, the effect of the tangent vector to a coordinate curve acting on a coordinate function is simply delta ij. It gives you 1 if you're talking of the same coordinate function, 0 if you're talking of a different coordinate function. And therefore, this quantity is nothing but xi at p. So, capital X acting on xi, the coordinate function, gives us capital Xi. So, this is basically an easy, quick way of finding out the ith component, so to speak, of the vector field. Now, it's very easy to see that if capital X is a smooth vector field, it's supposed to act on any smooth function and give rise to a smooth function. And small xi's are obviously differentiable functions. They are actually the most obvious differentiable functions that you can have. Capital X acting on xi, which gives you the capital Xi, must be differentiable. So all the component functions of a smooth vector field must be differentiable functions. Conversely, if all the capital Xi's are differentiable, and if f is a smooth function, then capital X acting on f, any smooth function, is basically capital Xi del del Xi acting on f, and that's nothing but the product of capital Xi with del f del Xi, according to the definition of a function multiplying a vector field. But notice that the moment you have this, it's a product of two smooth functions. Capital Xi is smooth by supposition, and since f is a smooth function, it has derivatives to all orders, which are themselves smooth, so del f del Xi is also smooth. And therefore, if all the coefficient functions capital X1 up to capital Xn are smooth functions, capital X must act on a smooth function f to produce another smooth function, and therefore capital X must belong to the set of all smooth vector fields. Now comes one very important result, which is sure to be familiar to all the physicists. This concerns the way in which these component functions change when you go from one chart to another. So for this, let us consider two charts u, phi and v, chi, which are both charts on M with a non-empty intersection of the domain. So u intersection v is non-empty. Now, if the corresponding coordinate functions corresponding to this chart u, phi are x1 up to xn, and the one corresponding to v, chi is x prime 1 up to x prime n, then for any capital X, any smooth function, capital X prime I will be given simply by capital X acting on the x prime I coordinate function. But capital X, remember, can be written down as capital Xj del del Xj. These are, of course, components corresponding to the original chart's vector fields. So, when this goes and acts on x prime I, according to whatever we had worked out before, this is nothing but the product of the function capital Xj with del del Xj acting on x prime I. Our notation for which is del x prime I del Xj. This particular way of transforming components of a vector field when you change your basis should be very, very familiar to physicists. This actually is a way in which physicists define contravariant vector fields. The so-called contravariant transformation of coordinates. But notice that you did not have to assume that as part of the definition of a special kind of vector field. It followed automatically from the geometric, or rather the algebraic definition of vectors from which we got this vector field definition.